It's the beginning of a new week in Foundations for Algorithms, and we're now at the pointy end of semester. But before we get into our material for this week, which is pretty exciting, we're going to get to some two-dimensional data structures. I first wanted to introduce another historical figure. This is Don Knuth. He is known as the father of algorithmic analysis. So although this time when we've been doing these big O proofs and these correctness proofs, he was really the father of that whole field and that whole area. Along with the theoretical side, though, he's also quite well known for these books, The Art of Computer Programming. And pretty much all the basic algorithms we're doing in this class, and many, many more, he formalized in these books. And so if you want to solve a particular problem and you don't know if there's already an algorithm for it, and it's a fairly typical kind of problem, check out these books, look through the index, and see it's very, very likely that he has an algorithm there for you. Don Knuth was also given a Chinese name in service of his contributions to international computer science, which Liam is going to pronounce for you. Gao Dena. And worked for the NSA as a cryptographer for a time as well. Thanks to his contributions to the field of computing overall, he is a Turing Award winner, one of a number that we've seen in this class. And to many of your chagrin, he is also the inventor of a very important mathematical, scientific, and computational typesetting system. Anyone know what I'm talking about? Typesetting system that we use in maths? LaTeX, yeah. So he invented TeX, which was the precursor to LaTeX. Now, along with his well-known formal side and the algorithms that he creates, he also had a kind of a fun side. And if you spot an error in one of his books, he will send you this check for $2.56. And while for a long time you could cash these checks, they're now just fun checks. But having one of these in your possession is considered to be a great honor. It means you've spotted a flaw in one of Don Knuth's books. So I encourage you, if sometime peruse through the books, see if you can find a bug. And if you can, come to me and let me know and show me your beautiful Don Knuth check. So that concludes our historical introduction to the week. But now we have a friend who I've asked here, a very important friend from the Melbourne Zoo, who's going to take the next segment of class. And so we have our friendly ape here, and he wants to know how long his descendants lived until. So in our typical C style, we're going to represent our friend the ape's question in a program. And here we have
the array is not sorted by the age. You can only just do linear search.
So we could use linear search. Remind me what that is. What do I do?
Check age entry, iterative.
Yeah, I go one by one down the list. And so I get to King Kong, he's 86. I get to King Louis, he's 13. I found my 13-year-old ape. So keep the microphone for a second. But this was a little slow. It was O of n time. So how did we find an item in a sorted list or array? There was a faster way to do this, wasn't there?
If there is sorted, you can just use the binary search.
Binary search, okay, that's correct. But then we have the problem of how do we get our things sorted in the first place. If we look at our array, it's not entirely clear what it means to sort an array of apes. I mean, we could sort them alphabetically, we could sort them by weight, we could sort them by age, ascending or descending. We haven't really been clear, and I haven't been clear up to this point what it means to sort. So when I say do binary search on an ape, we first have to define that. So we have to answer what it means to sort. And to answer what it means to sort, we need to answer another question first. If I have, let's say I have ape A and ape B, how do I know the correct order for the apes? Aruki, do you want to pass the microphone one along? No, just pass it one along. What was your name? Yulong? Okay, so what do I need to know in order to sort something? So if I have ape A and ape B, what do I need to be able to do in order to sort an array full of apes? And you've got a microphone, so use it.
Asking.
Well, ASCII is just how to put their name into the computer. Let's think in the real world. If I ask you, which ape is greater, ape A or ape B? What are you going to ask me first? Have I asked you a reasonable question?
It's not specific.
It's not specific enough. What information did I need to give you?
What do you mean by ape A and ape B?
So what do I mean by ape A and ape B? But what was the other part of my question? Which ape is greater? And what does it mean for an ape to be greater? So we need to have some kind of ordering of apes. So from greatest to least great ape, by whatever that might mean. And that introduces a notion of comparison. Now, of course, we could go all formal and mathematical and talk about ordering in a formal, rigorous sense, but we're computer scientists, and we're first-year computer scientists, so for today we're not going to worry too much about our mathematical definition and just ask that we define these three properties. We're going to need to have some way to say, are the apes equal? Is one ape greater than the other, or is one ape smaller than the other? And we can define this using a function. We can have a comparison function, which given ape A and ape B says which ape is bigger and which ape is smaller. And we can define that in lots of different ways. We could say the bigger ape is the one that has the higher age, or the bigger ape is the one whose name comes later in the alphabet. So here's our structure, and now we're going to write a comparison function momentarily. So we need this function to compare things that don't naturally have an order. We didn't need to write a comparison function for numbers. Like if I said I have two numbers A and B, and I ask you which number is greater, you know what that means, right? Yeah, Yulong has got a notion of what it means for numbers to be ordered, but not a notion of what it means for apes to be ordered. So we need to write a function. Now, we could go off on our own and start writing all our own functionality and defining what it means for comparison, but this seems like a pretty typical thing, so the C standard library comes with a built-in way to talk about comparisons, and this is the manual for the C library. So along with the man pages for your operating system, the C standard library, all those header files that we include, also has a manual. And we can go through the manual, and it's got this entry on defining a comparison function. And down at the bottom here, it says there's even a type, comparison function T, const void star, const void star. Now, this syntax looks pretty weird. It's something we haven't seen before. But the basic idea is we need to define a sorting function that can swap out what type of comparison it uses. Because if we're going to sort apes, we need to be able to sort apes by, say, age. If we're going to sort strings, we need a way to sort strings. If we're going to sort numbers, we need a way to sort numbers. So we're going to want some mechanism using this type of comparison function where we can swap the function in and out. And this is why this syntax looks like it does, and we'll get to the details of that in just a moment. So here is a function called qsort. Now, what does qsort probably stand for? Do you want to pass the microphone to Ashwin? We're just going to do microphone passing today, so if you're in the line of fire. Ashwin, what does qsort stand for?
Quicksort.
Quicksort? That would be correct, except the manual has this little addendum at the bottom. The qsort function derives its name from the fact that it was originally implemented using the quicksort algorithm. It isn't anymore. But why have we been bothering writing our own sorting algorithm? There's one built into the C standard library. And we can see up here, it takes a couple of parameters. It takes an array that we want to sort. It takes the number of elements in the array, the size of each element in the array, and then it takes one additional weird thing. It takes comparison function T, compare. So what is this? Remember we said we needed to write a function which tells our program how to do the comparison? We're going to give the qsort function another function. We're going to tell it this is where to go, this is the function to go to, if you want to know how to compare these things. So now if we go back, this comparison function suddenly makes sense. What it is it's going to be a pointer to another function. It's going to be a pointer to a function that tells you how to compare the type of things that we're giving qsort in the array. So said plainly, this is just a function pointer. It's a pointer to a function. Now, where does a pointer to a function point to? Let's go back to our memory map that we've seen a few different times. We have our stack, and Ashwin, what goes on the stack? Just remind me.
The values that we store.
Yeah, normal variables. What goes in the heap?
Dynamic memory and function.
Dynamic memory. So what function do we use when we're allocating dynamic memory?
Malloc?
Yeah, so anytime we malloc something, that goes in the heap. Do you remember what's in the text section? Okay, so we'll take that as a pass. Inside the text section is the actual code of your program. So remember, your code has to be stored somewhere on the computer as well. And when the computer runs your code, it needs to know where in its own memory to find the next instruction. So inside the computer's memory, the text section is actually reserved for the code of your program itself. And just like we can have a pointer from the stack into the heap, we can have a pointer variable that points to some dynamic memory. We can also have a pointer that points from the stack into the text. So it's pointing from the stack. It's a variable that you create inside a function, just like any other, that points to some part of the program. And we'll see how to use this in just a moment in our code demo. And we're going to use it as a starting place to explore our function pointers. How do we declare a function pointer? Write the function prototype as you would normally, but put it inside the body of your code somewhere. Then put a parentheses with a star around the name of the function, and that's it. That's all there is to it. So C has some odd syntactical choices around function pointers. Among them, it's going to automatically dereference them. I mean, you can dereference them if you like, but if you call the function using that like bracket syntax with the arguments, it'll automatically call it for you. It'll automatically dereference. C will also automatically take the address of a function when you start setting up function pointers. And we'll go through this. We've got some examples on Ed, some in your tutorials, and we'll do one or two of them right now. So this is our first one here. funcpoint.c, and I'm not going to be able to zoom in on it, unfortunately, because I haven't figured out how to do that capability on the iPad. But the spanner icon. Oh, there we are. Zoom. There we go. Yep. Okay. So here we have our very first function pointer. What it is we have a function pointer called f. That doesn't mean the function that it points to is called f. Just like you can have a pointer called cat pointer, and the cat pointer points to a cat. But the cat pointer and the cat are separate things. In this case, we have a function pointer f. And our function pointer f, we're going to set it to point to something called square root. We'll talk about what square root is in a second when we scroll up. So what type is the function pointer? Because we have to declare what type of function it's going to point to. It's going to point to a function that returns a double, and it takes an argument of a double. So if we think about how we wrote that in the first place, so let's imagine we're writing the function prototype for a square root function. Function prototype might look something like this. That's our function prototype. And to convert it to a function pointer, we put brackets around the name of the function, and that's going to be the name of our pointer. We can remove the name of the arguments, because whatever function we point to is going to decide what those names are, and then we're done. And this comma over here is just essentially the same thing as putting that on a new line. So we could do that, and our program would be perfectly fine. OK. I'm struggling to use the iPad for this. Going to get a keyboard next week. OK. So now we set f to be a square root function. Now this is what I said before. Normally you'd have to take the address of something if we're using a pointer. Like square root is a function, and if it's a function pointer, we have to get the address of the function. But C kind of hides that from us and allows us to just use square root directly. Then we're going to run our function f. So when I run function f, Ricky, do you want to, Ashwin, do you want to pass it on one more? When I run my function f, what function am I really running here? And what was your name?
Lucas.
Lucas.
It'll run the square root function?
Yeah, it'll run the square root function, because our function pointer f is pointing to the square root function. And our square root function, let's look in our code. Oh, the square root function is included in math.h. So C already knows what this square root function is and where to find it. and we set the function pointer here. Now, Lucas, what happens when I call f of x over here?
It'll run the sine function,
Run the sine function because I've changed what the pointer is pointing to, and then,
the log function.
and will this last line work? What do we think?
Because it's just dereferencing it, isn't it? It would still work, right?
Yeah, I'm dereferencing the function pointer and then using the call syntax, but as I said on my prior slide, C automatically dereferences function pointers for you, but you can do it if you like, so it'll still work. I think we're ready to give it a run. It's going to be a little small, but should still work. What was it called? Func point. There we go, and you can see the f of x change in each instance to calculate the square root of 2, then the sine of 2, then the log of 2, and then the log of 2 again. So there's our first demo. That gives us a pretty simple function pointer. Let's ramp up the complexity one notch and look at it as where we use it as an argument. So in this case, our main function, let's scroll down to it. We're going to have a whole bunch of different items in two arrays. We're going to have a double array and a string array. And what we want to do is find out if each of our arrays are sorted. Now remember what I said before about like sorting apes? The same kind of thing applies to sorting strings. There's no inherent notion of what it means to sort a string. But in this class so far, we've talked about lexicographic sorting of strings. So where the strings are sorted by looking at the order in the alphabet where successive letters appear. So we want to be able to use the same isSorted function for both of them that does the baseline kind of thing of telling us whether an array is sorted. However, to use isSorted, we have to define the way that ordering works. Again, a comparison function. So what I have here is I've written two different functions that are both going to be different comparison functions. So one comparison function is for doubles and just compares two doubles, and one of them compares strings. So let's look at our comparison functions. So string ascending runs strcmp, which we've seen before. It just compares two strings. And our string descending switches this to do the negative of string comparison. Because remember, we have the way that the comparison functions work is they're less than 0 for one order, greater than 0 for the other order, and 0 if the two things are equal. So by putting a negative sign, all we're doing is flipping the ordering from ascending to descending. And then our double function, we've just done d2 minus d1 because they're both doubles. So if we dereference a double pointer and dereference the other double and take the difference, that'll give us a comparison for descending. And for ascending, just the opposite. OK, now let's look at our function prototype for isSorted. So we take in some array of elements, the number of elements, which is going to be a size t type, the size of each element so that we know how far along in memory we have to go to get to the next item. And then we have another function pointer. So Lucas, what can you tell me about this function pointer? What can you read off from the signature?
So it's dereferencing the compare function, and it takes into, I'm actually not sure.
So kind of on the right track with part of it, but remember this is a declaration, not a statement that's actually assigning something or running something. So when we talk about our syntax for declaring function pointers, what did I say? How do we declare a function pointer?
You have the star and the name in the parentheses.
Yeah. So that's what I've done here, isn't it? Yeah. So this means I have a function pointer that's called CMP, and it's just like A and LM and size. When you go inside the isSorted function, you can use CMP like a variable, and the variable will be set as one of the arguments to the function. So we have CMP. What's its return type?
Void.
What's its return type?
Int.
Int. And what are its two arguments?
Void.
A void pointer and
Another void.
a void pointer. Now, why do you think we use a void pointer?
Because the compare is altering the pointers, but it's not returning anything.
So do we know ahead of time what type those two things are going to be? No, so we're going to use a placeholder type. We're going to use a void pointer type to say, we know it's going to be memory. It's a pointer to something. But we don't know what it's a pointer to yet. And the compare function is actually going to define for us later on the way that we should convert these void pointers into some other object. So if we see over here, we can use the void pointers like a char star star pointer, like a pointer to a string, by casting it over there. And here we have, is this an implicit cast or an explicit cast? Lucas, is this an implicit cast or an explicit cast?
Implicit.
It's implicit because we haven't added that little bracket saying what type it should go to on the right-hand side. We just have it on the left-hand side. But this will be fine. We can convert our void pointers like that. We might just get a compiler warning depending on the flags that you've put in. So now let's look at our isSorted function. We have a, what's this, Lucas? Or do you want to pass the microphone on? Are you done? It was Afan, wasn't it? Yes. Yeah. OK. So what do I have here on the first line of isSorted?
Char AP at that time, 55.
What is it? Char?
Char, pointer AP.
It's a pointer to a character, right? And a pointer to a character, remember that that's the smallest kind of pointer we have. That'll move one step along at a time when we use pointer arithmetic. OK, so let's keep that in mind. That pointer can move one chunk in memory along at a time. OK, so while there are more than one elements in our thing, OK, obviously if there's only one element, the thing's sorted. If comparison AP and then AP plus size is bigger than 0, then they're out of order because they should be the other way around. So we're calling our comparison function with AP and AP plus size. So why are we using AP and AP plus size? Afan, do you have an idea?
So AP is just the first point and AP plus size is just one after that.
AP points to the very first address of in the array, and AP plus size, what's that going to point to?
The next one.
Is it going to point to the next address in memory in the array? Or that doesn't sound quite right, because let's say we have an integer. An integer is at the first byte, and the same integer is also at the second byte, and at the third byte, and at the fourth byte. So what is size doing here? So let's say that we're using integers that are 4 bytes long, and so size is 4 bytes. What does AP plus size take us to?
The next memory pointer.
It doesn't take us to the next pointer because that would be 1 along. It takes us to the next object of that type in the array. So if we have an array of integers and we have a pointer that will increment 1 byte at a time, we want to start at the very first byte, and then we want to skip 4 bytes along to get to the next integer. And then we're going to want to skip to the next 4 bytes along to get to the next integer. And so that's essentially what we're doing here. At the end of the while loop, we're going to set our pointer to start at the next element along, and then reduce the number of elements we have left to look at. So this gives us our isSorted function. There we go. And you can see array X is ascending and array S is descending, as we had above. If you look at array S, wombat, wallaby, quoll, quokka, koala, kangaroo, goanna, bilby is in reverse order from later in the alphabet to earlier in the alphabet, whereas X is going from 1 to 3 to 7 to 8 to 9. It's in ascending order. And by using the function pointer, we could have one function that defines the logic for sorted and just swap out this little comparison function, which determines how to compare two separate things of different types. Or how to compare things of the same type for different types. Now we finally get to actually using qsort to do our apes. So here I have, let's see if I can, I have my 3 apes there, Rafiki, Mojo, Jojo, and King Louie. I have 3 of them, and I'm going to call qsort, which is the function we saw before in the manual. I'm going to give it just the same as we did before for our isSorted function. The first argument is the array. The second argument is how many items in the array. The third argument is how large each element in the array is. And then the last one is our comparison function. So let's scroll up. There's our comparison function. Our comparison function is dereferencing the void star and casting it to an apt type. Once it's casted it to an apt type, so you can see the cast happens first, which is why it's got parentheses around, around the name of the variable. So we do our cast. Once we've cast the void pointer, then we can get the age of the first one. We do the same thing to the second one. We cast it, and then we get the age element, and that is our, the entirety of our function. So then it's as before, we do qsort, so I'm printing it before, I'm running qsort, I'm printing it after, and then I'm going to use one more function, which looks very similar again, bsearch. Now, fun, what does bsearch do? Yeah, it's going to be binary search. So it says it searches an array of NL objects. We can guess what it does, but let's just look at the function signature and see if we can figure it out. So it gives us back a void star. So why is it giving us back a void star? But what should binary search return if it's successful?
Int 1.
Should it return int 1? Or what's the goal of binary search?
If like finding the actual value.
Yeah, we want to find the item. And so void star will give us a pointer to the item when it's successfully found it. Okay? Then we have to tell binary search what we're actually looking for. So for example, if you want to find the ape whose bar mitzvah it is, who's 13 in our array of apes, you have to say the thing that we're looking for is the number 13 inside the ape struct. And then again, the thing that we're searching in, the number of elements in it, the size of each element, and then our comparison function. So let's actually go ahead and use this down here. This is the key. I've created another ape t type, and in this case, I'm looking for an ape that matches, that's going to match the number 13. But you might say, well, wouldn't it just match things that also have a null string in there? Like what happened if I type the name Tarzan? Now, Tarzan's not an ape, but I'm short of ape names off the top of my head this moment. And you'd say, well, if I'm using Tarzan and 13 as the key, how do I know that it's not going to return me Tarzan instead of the bar mitzvah ape? Well, the way that it does that is we're going to use our comparison function to determine when the thing that we're looking for is equal to the item that we're currently looking at. And ape age ascending is a function pointer that doesn't look at the name of the ape. All it does, if we look up again, it looks at the age of the ape. So even though our key has a name in it, the only thing that's going to be examined by the comparison function is the age over here. So we do bsearch. The bar mitzvah ape is going to be equal to the result of bsearch. If it's null, then we haven't found the bar mitzvah ape. And if it's not null, then we have found it, and we can print the name and the age of the bar mitzvah ape. So let's run it. And no surprises, we now have an array in, oh, I didn't put a space between the array unsorted and sorted. So you can see it started off as 10, 13, 8. Then it went to 8, 10, 13, which is the correct order. And at the end, it found Mojo Jojo, who is in fact the bar mitzvah ape. So we've now got a pretty powerful tool for polymorphism. Again, this idea of being able to do the same type of operation, but with different data types, with different C types. So we can do sorting of precedents, apes, ages, strings, and the way we can easily do this and reuse our code is by using function pointers to swap out that key bit of logic that changes depending on what the type is. So this is all well and good. We can do binary search. We can find the bar mitzvah ape. But what if we need to find items over and over? Now, grandfather ape is happy he's found his 13-year-old son, but he wants to find his 22-year-old son or daughter. And we're going to repeat this process again and again. So let's pass on the microphone one more. Was it Leo? No, what was your name again? Bruce. Oh, sorry. Where's Leo? Are you here today? There. Oh, right behind. Okay, Bruce, turn the microphone on. Okay, so give me one way that I could now find which of the apes lived till 22.
You could iterate through the list of the apes and then stop when you find.
So that would be our linear search. And Haruki, you were telling me before there was a better way than linear search. What did Haruki say before? What did we just do in our code demo?
Binary search.
Binary search, so that required us to sort it and then do binary search. But remember, the ape before was asking us for the one that's 13, and now he's asked us for the one that's 22. Do you think there's some way that we can do this a bit more efficiently than like doing binary search, sorting, binary search again? What happens if a new ape joins the family? Now what do I do?
You see if its age is larger or smaller than your current middle,
And then what am I going to do?
and then you gotta put it on a right or the left.
So wait, right or left? Oh, you mean on the right or left in the array?
Yeah.
Okay, so we're going to need to like do this complicated thing and start reshuffling our array. And this whole procedure is getting a little tricky to keep track of. It's going to require a lot of array operations to copy things around. Maybe there's a better way of doing this if we're going to repeat stuff over and over. And that is going to be the remainder of today's lecture, probably tomorrow's lecture, and maybe even some of the last one of the week. So Bruce, you can switch that on mute for the minute. So we have a new data structure approaching. This is a tree. Now this is not a binary search tree. It is not a heap. This is just a tree. Now the funny thing about this tree is that we're going to call the thing at the very top the root, and the thing at the very bottom, all those things at the bottom that are coming off the end, we're going to call those the leaves. So this is a very strange type of tree, but nonetheless, it's our tree. And these are the characters who we are going to be entertaining for the rest of the week. So a tree is just like a linked list, except what's a little different here, Yuvani? What's different from a linked list about our tree?
It goes down.
Well, it goes down, but we could put the tree on its side and it would still be a tree. What's different about it? Each thing in our linked list was connected to how many items? 1, and how many things is everything connected to here? 2. But you might say, I'm a clever person. I was paying attention to you last week. You were talking about doubly linked lists. So you could have a pointer going forwards and going backwards. But there's something that's also different about here. If we think about the way at least that I've depicted it here, our pointers don't go forwards and backwards. Instead, they're arranged to point to a hierarchy of things. So something is at the top of the hierarchy and some things are at the bottom of the hierarchy. And at each step, you can take you have a decision between 2 things of where to go next in your hierarchy. So right now, our hierarchy doesn't make much sense, but we could start putting some rules on the organization of our tree. So right now, it's just a free-for-all. Everyone's going randomly. We can still write a bit of C code to represent this, though. This is our C code. So just like we had our linked list node that had a pointer to next, we now have a pointer to left and a pointer to right. Now, obviously, there's no actual left and actual right inside a computer. These are just ways for us to build an abstraction of what the tree is. So we can imagine this image and imagine it's stored inside the computer, even though in reality it's just a set of pointers. So we have our data, we have a pointer to the thing on the left, the node on the left, and a pointer to a thing on the right. Now, just as before in our linked list, this is a recursive data structure because inside every node, there are more nodes. And remember, you have to lay out your type defs and your structure just right to actually make it work, but hopefully you'll get some practice with that in your next assignment. So what is the runtime to find the oldest monkey in our hierarchy like this? And Bruce, we're going to stay with you, so turn on your microphone again.
I think it's O of 1.
O of 1? So you're telling me that it's just a fixed number of steps to find the oldest monkey? Can you tell me what your thought was? How did you get there?
Actually, not bad. I think it's how many times you have to go to the left, assuming if you put the larger number to the left.
Is that what I've done here, though?
I think so. So, middle, 30, just larger than 20 to the left.
This one should not be ordered. No, this one is not ordered like that. If you take a look at it, it's very clearly not in order. So how am I going to find the oldest monkey?
Okay, so you gotta start from the top.
Yeah.
And then you look left and right.
Okay, let's start with looking left. Okay, now where should I look?
I get what you mean.
Just keep going with me. Where do I look now?
And then you look right.
There's nothing on the left on this one. The dotted lines mean nothing there. You'll have to forgive where some of the graphics are. So
So you look right.
look on the right.
And then you gotta go to the left.
Okay. Do I know that I found the oldest monkey yet?
Not really.
No. Why can't, have I not found the oldest monkey for sure yet? Assuming that we haven't looked at the right side yet. That's all blank to us.
Because you know that the previous one was larger than the current one.
Another way of saying it is we know there's no order in our tree. And so the oldest monkey could be anywhere. And we've only looked through part of it, so it's possible that the oldest one is in the bit we looked at, but it's also possible that it's in the bit we haven't looked at. So what do? I'm at number 14, and I've got no children. I mean, by children, I should say what I mean by that. I am childless, but what I mean in this instance is we can say that every node has two children. It's got a left child and a right child. And this is just computer speak for saying the two objects that come off of any given node, or more than two maybe if you're a particularly fruitful tree. Okay, so we are at, this is a binary tree because it's only two children, but we could have a ternary tree with 3 children. But let's stick to binary trees. Okay, Bruce, so I'm at 14 and I'm alone and childless and old. What do?
You can go back.
I can go back, okay. So where do I go back to?
You go back to 27.
Okay, I can go back to 27, and then from 27,
Go back to 33.
go back to 33, and from 33,
To 20.
yeah, Afan, I think I know what question you're going to ask, but go ahead and ask it.
Can you really go back?
Can you really go back? Okay, so there are 2 answers to this question. So let me go back on my slides at least, and you can answer that question for me. Can you go back from this data structure to the parent? Take the microphone for a second. Yeah?
Depends on how you define it.
Okay, so let's say we're defining it. Oh, I was one side to. There, where did my struct go? There we are. So let's say we're defining it this way. Can you go back?
No.
Do you have a way that you could go back if you're writing a whole program around this?
If you had a parent link.
So one thing you could do is you could put a parent link in there, and that might not be a bad idea. This is just like our doubly linked list where you have a pointer to previous. What's another way that we could go back? You get to write the whole program. So what could you do right before you're about to go forward and down the tree?
Or you store your previous parent.
You could store your previous parent. Now, if we're doing a recursive function, we could be quite clever. And if every function call stores its parent and then does another level of recursion, then at each level, when you exit the recursion, you'll be back at your parent. But we know that recursion, everything that can be done with recursion can be done with iteration. And so just like we're using the call stack of different functions on top of each other, we could also use a data structure stack to store all the parents and then go back that way. But that's a little beyond what we're going to discuss for today, but really good point, and you can hand it back to, let's give Max a go, I think. Oh, no, wait, Bruce, I wasn't finished with you. We'll get to you, Max, but we'll take another minute. Okay, so Bruce, we've gone back, and we're back at our root node again. Now what do?
You go to your right.
Go to my right.
Go to the left. And you take a peek at the right, and then take a peek at the left.
But your algorithm thus far was going left first, right? So we should probably do that.
Okay.
Let's go left first.
To the left. And then I'll go to the right again.
Go to the right.
And I see that my current is smaller than the previous one, so I go back.
Well, it's not just that the next one is smaller. That doesn't make a difference because the biggest one could be anywhere. But we see that node 21, what does it not have?
Any left or right.
Doesn't have any children. Node 21 is just like I am, old and soulless and childless. So we go back. Do we stop here? We've already seen 40, which is the biggest one.
You can still go back one more time,
Yeah, we still need to go back. Why do I still need to go back?
because you haven't gone through all the children.
I haven't been through the entire tree, and I don't know where the largest item is. I'm a computer, and I haven't looked at 34. For all I know, that node there could be the bigger one. So now we go back, and we look at 34, and now what can you say?
Okay, now I know that 34 is not bigger than my current max,
Yep, current max was,
40.
yep, so we're done, right? Okay, how many nodes did we have to look at for this to work? If there are n nodes, how many nodes did we look at?
And nodes.
N nodes. So what's the runtime?
Oh,
O of n. Okay, so we haven't really gotten much of an improvement here. This is not binary search. Binary search would have been better. But we can do a little better, and Max is going to give us some ideas. So this was slow, and definitely slower than binary search. But what can you tell us? What made binary search actually work?
Well, I'm thinking that you cut out half of what you look at every time you go to the next check, I guess.
So is that giving you any ideas about how we could structure our tree?
We could do like the middle one, everything on the left child is smaller than it, and everything on the right child is larger than it.
Yeah, so this is really natural actually when you think about it. Just like binary search had this arrangement property, which meant we could throw out half because half was smaller and the other half was, say, we figure out which half we can throw out based on comparing with the item that we're looking for. We can do the same thing with our trees. So the way we arranged the array, how did we have to arrange an array for binary to work? For binary search to work? Yeah, we needed to have, it needed to be sorted is another way of saying that. So binary search required sorting, so we can do the same thing with our trees. We can arrange our tree in such a special way, and we'll talk about how to build one of these trees, such that there is a partial ordering of the elements. That's fast to construct. So we have to develop what an order means, and then make our tree reflect this order. So we could do it in fully sorted, we could do it partially sorted, we could come up with a bunch of different ways, but the core idea is at each step we have to be able to throw out half of the tree and only go down the other half. And Max is bang on point. So this is what we call a binary search tree. A binary tree is any tree where every node can have two possible children, but a binary search tree is going to have the property that Max described for us, where the right subtree is greater than or equal to the parent, which is greater than or equal to the left subtree. So we have a nice ordering. Now, Max, would it be okay to flip this order? Would that be a problem?
Can't see why
No.
not.
It really doesn't matter which way we do the ordering. One way is ascending, one way is descending. They're both perfectly legitimate orders. So now, keep with the microphone. I've got a task for you. Here is my binary search tree. And now I want to find the oldest ape. So what's the runtime for it? Let's. Do you want to take a guess before we go and do it?
Something like n log n.
N log n? Why is it n log n?
Just a guess.
Okay. What do we know about throwing half of the thing away each time? Let's see. Okay. Let's see if Max is right about our log2n. Okay, here is our binary search tree. And I'm looking for the fastest ape, the oldest ape.
Alright, so we're not going to check the left.
Not going to check the left.
Smaller. Go to the right.
Yep.
And then we're not going to check the left again either. We go to the right.
Yep.
And we check the left. Actually, no, we're not going to check the left. Why would we do that? We're at the oldest ape.
Yep, we're at the oldest ape. Now, how many levels did we have to go down? We had to go down 2 different levels, and we know that all we're going to do, let's say there are 5 levels to the tree, what is the most amount of steps that we're going to have to take?
2 to the 5. Yeah.
2 to the 5? We're just going to have to take 5 steps, because each time we go, every time we take a move, we're going to go down a level. There's no backtracking, and we already know how to choose between the left and the right. We're always going to choose the right. Keep going right, keep going right, keep going right. That'll find your element. So that gives us a little bit of information. Now let's do it and let's try and find a particular element. Let's say I want to find the number 22. How am I going to find 22?
So we go right first because 22 is greater.
Yep, 22 is greater than 20.
Smaller than 33.
Yep.
And left again because it's smaller than 27.
And there we are. And how many steps did we take? We took 3 steps because that's how far it was down in the tree. What's the maximum it could have been down in this tree? Okay, so let's assume that on average, our tree is going to have all the nodes distributed so that the tree is complete. And what do I mean by complete is every node has 2 children. And so it's fully fleshed out. It's a tree with all its leaves present. If I have all my leaves present, what's the maximum height of the tree going to be? So the first level has 1 node, and then the second level has 2 nodes, and then the third level has 4 nodes. So if I ask how many levels are there for n nodes?
Log 2n.
Yeah, log 2n. And so for an average tree where all the elements are truly random and they're distributed in a way such that our tree ends up being complete, we get a log 2n runtime. What is the worst case?
It's right at the end.
It's right at the end, and we'll get to that in a second. I'll come back to you. Okay, so we did this. We found the APU is 22. And this was O of h average case, where h is the height of the tree, assuming that our items are truly distributed in a random fashion and there's no reason to suspect that they're clustered in one particular way or another. We're going to get O of log n average case for both finding the maximum and for finding a specific element. So we now have this, but we have a worst case that we haven't talked about. If you were going to arrange all the elements in a tree such that it took as long as possible to find the maximum, how would you arrange them?
I just jumble them up as much as possible, and I put the maximum one as far away from the first.
So let's say we have n nodes. How far away can the biggest one be? 2 to the n? There are only n elements.
Log 2n.
So that's if our tree is beautiful and that's the minimum number of, the average number of steps.
Yeah.
What about the worst? Can you think of an arrangement of things? So let's say I have, let's make it 4 items, right? What is the maximum depth? What are the maximum number of steps you would have to take?
With 4 items.
Yeah? How many jumps could I make?
And then split it 2. And then
Well, let's say instead of splitting into 2, I only use one of the sides.
you do two jumps then, wouldn't you?
So I have a jump from the first element to the second element, a jump from the second to the third, a jump from the third to the fourth. In fact, that's going to be O of n. What I've done is I've created not a tree, I mean it is a tree, but it's a stick because none of the left children are filled out. And so it turns out in the worst case, this devolves to O of n because we have a tree that's arranged in the worst possible way for, in the worst possible way for our runtime. So thank you very much, Max. You can pass the microphone on. Actually, let's pass it all the way back to Victor at the back and get his question. Oh, yeah.
Go back to that other tree. Like, what if there was, see where it's 22?
Take the microphone.
So see where it says where it's 22?
Yeah.
Couldn't there be like a 50 to the right of 22, and that would still be greater than 22?
So that would violate our rule for the subtrees. So it's not just that the parent has to be well ordered with respects to its children. It's that the entire subtree, which means everything under a given node, also has to obey this property. So if you look at everything under 33, everything under 33 is smaller than 33. But what you were talking about, we will get to in a lecture soon, talking about some ways of relaxing this and making it a little less strict. That'll give us some additional properties. So good question. Now let's pass it back to Victor. And Ruben hiding right in front of him. Oh, and we're just about out of time. So we'll take this question and then we're just about done.
Right, so my question was, with the stick before, isn't that essentially a linked list?
Yeah, a stick is essentially a linked list. Let's go to our stick. This is essentially a linked list, except we're wasted a whole lot of memory because each node has left pointers that we're not using. And so to finish it off, if we have n items, we can have a maximum height of n nodes, which means that our find maximum and our search is going to be worst case n. For random input, our average depth was going to be O of log n, but assuming that just like the linked list, we're going to have things coming and going and joining and leaving, and we're going to be modifying our data structure, we can't possibly have it beautifully arranged. As things come in, we're going to need to do something clever, and we will talk about that more next lecture. I will see you all tomorrow.